If the amateur astronomer today would like to obtain a telescope of some significant size and light gathering power, it's a pretty easy thing to do, if one's pockets are sufficiently deep. A number of fine companies are willing to sell 16-inch or even larger reflecting telescopes with excellent computer-controlled guidance systems that are, in almost every way, identical to all of the other same types of telescopes sold by the same company. These scopes can be set up in a short period of time, and one could be looking at any number of objects with a stunning level of clarity and resolution. If that amateur astronomer wanted to do some research, say in planetary photometry or variable star brightness, there are easy to set up photometers and CCD cameras that can be mounted on the instruments, and, with a little patience and practice, they will begin to bring in data that is of high quality, assuming some reasonable observing protocol is followed. While all of this does take some education, a little bit of training, along with time spent in the field getting to know a bit about the way the instruments work in a real-world setting, these are skills that can be acquired in just a few months of dedicated effort. With these modest-sized scopes, with their computer-controlled gear drives and digital light-gathering devices, it's no longer required that the astronomer be a tinkerer and an instrument maker. Those skills are now needed only in the realm of the truly large telescopes found at the tops of the world's tallest mountains, overlooking the still, cool air of the oceans. Yet, even in these great instruments, several meters in objective size, mostly they're run remotely these days. No one actually looks through them anymore, at least not with their eyes. Now, instrument packages are designed to take advantages of each telescope's unique design and capabilities. This is now where the artistry of astronomical observation lies, in the ability to coax from metal, glass, and electronics images and data not previously available, and, from that data, uncover and discover new secrets once hidden away from the human mind. But in one's own backyard, it's still possible to experience a bit of what earlier astronomers once did as their careers. Through the late 1800s and early 1900s, the reflecting telescope experienced a renaissance both in use and design that made it the preferred instruments of those seeking to take truly long images of the faintest objects. The earliest versions were actually not that much bigger of what can be obtained through the companies that more or less mass-produce reflecting telescopes, but unlike these identical optical systems, back then each telescope was unique. Each could be said to have its own personality, its own quirks and idiosyncrasies, owing to the singular manufacture of its mirrors and drive systems. Even more unique than the telescopes, though, were the cameras and spectrometers that were attached to them to gather light in a way that the eye never could. As each was manufactured with different glass or to use a different type of photographic emulsion, each had observations it could make and others where it would struggle. Some had glass that absorbed yellow frequencies of light while being particularly sensitive to the blue wavelengths. Others would be able to peer into the infrared or ultraviolet part of the spectrum in ways that human senses never would be able to. For all of these different cutting-edge instrument systems, designed and built before the modern period of standardization, it was the astronomer who had to learn their use, their setup, the rig, and all of the other things as effectively as possible to do research in a way no one else could. These men, and in a few rare cases women, became artists at coaxing from their telescopes information beyond what they had originally been designed to do. Much like a musician with a one-of-a-kind violin, who can draw forth from its strings a timbre and vibrato that transforms even the most common piece of music into something sublime and revelatory. This week on the Scientific Odyssey, we will take a look at the lives and the work of some of those earthbound explorers of the cosmos, whose expertise with the first large reflecting telescopes opened the way for even greater instruments and discoveries at places like Mount Wilson, Mount Palomar, and the Kitt Peak National Observatory. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 43.1, Supplemental-Masters of Reflection. If you want to talk about reflecting telescopes, the line, of course, goes back to Isaac Newton, who built the first working version of a reflecting telescope using a spherical mirror of about 6 inches of size as the objective element in around 1666-1667. This design was improved on by a number of other contemporaries, including men like Philip Gregory and John Hadley, who replaced Newton's spherical objective with a parabolic mirror, eliminating one of the two significant forms of distortion, something that we talked about before, known as spherical aberration. Now, during this period, however, reflectors occupied a sort of second spot to refracting telescopes for the simple reason that the mirror, made entirely of metal, tended to be harder to make than glass lenses and tarnished quickly, requiring their frequent removal for repolishing. Additionally, the early alloys used to make the mirrors tended to not reflect all of the different wavelengths of light and thus gave monochromatic images. Nevertheless, there were some advantages to reflecting telescopes, and men like William Herschel turned to making high-quality mirrors in increasing size until, in 1789, he built his 40-foot telescope with the 48-inch primary mirror. While this instrument was used occasionally, its large size made it difficult to point, and this limited its effectiveness, especially given Herschel's research program. This, however, didn't stop William Parsons, the third Earl of Rosse, from building an even larger reflector at his estate, Birr Castle, outside of Parsonstown in the center of Ireland. The Leviathan of Parsonstown, as it was called, was a Newtonian reflector with a primary mirror some 72 inches in diameter. That's 6 feet, if you want to really kind of count it out, and a focal length of 54 feet. The whole telescope weighed in at about 12 tons and required two huge 50-foot tall stone structures on either side to be built to both raise and lower the telescope and to support the observer in the various positions required to make observations. In this, Parsons invested significant resources to create a way to more easily raise and lower the telescope using both chains and a rack and pinion mechanical system that overcame many of the obstacles Herschel had faced. Finished in 1845, the purpose of the instrument was to answer a question Herschel had been trying to figure out, and that was whether various nebulas he had observed were just clouds of gas and dust viewed from a closer distance or collections of stars seen from further away. Parsons, understanding that the instrument was going to be large and difficult to manage, had assembled a group of assistants to help him in his researches, and so the telescope was able to be used more extensively to examine the various nebulae Herschel had discovered, as well as to extend his catalog somewhat. The most important thing found by Parsons was that there seemed to be a distinction between types of nebula, with some showing no indication of having stars, while others clearly did. In particular, there was a certain class of nebula that showed spiral structure, thus indicating, as Parsons put it, the presence of dynamical forces influencing their structure. Finally, he was able to resolve that some of these spiral nebulae, most notably M51, now known as the Whirlpool Galaxy but then more the Whirlpool Nebula, did consist of stars. Unfortunately, the location of the telescope in damp and windy Ireland limited its effectiveness, as did the inherent issues with all reflecting telescopes of that period. Nowhere were these shortcomings more profoundly illustrated than in what's known as the Melbourne Reflector. Built in 1868 for the Melbourne Observatory in Australia to observe the southern skies, the telescope used a new geometry known as a Cassegrain design to place a 48-inch mirror in a much shorter and more manageable structure that could be counterweighted and steered much more effectively. Now, to digress here briefly, let me take just a few minutes to talk about telescope design, as it'll be important later on in the episode. When you look at the light path for a refractor, the way the light comes in is it all comes into the telescope at the objective at the front end of the telescope and exits out the eyepiece at the back, meaning that if you want a lot of magnification, you have to have a long tube to give a long focal length. As refractors got bigger, this meant that they got really expensive really fast, because not only did your tube cost more, the tube that holds the two lenses on either end, due to its greater length, but so did everything else. Your observatory space that housed the telescope, as well as its floor, and the dome that covered it all, had to get a lot larger to allow for the telescope to swing to any position you wanted to observe from, anything from the horizon up to the zenith directly overhead. As photography began to come to the fore in astronomy, these long focal lengths created other problems as well. One way to think of a telescope when we talk about photography is that when the telescope is mounted to the camera, it really acts as a great big front lens. The problem, though, is that really long focal lengths give big f-stop numbers, which means that the pictures take a long time to expose. Now, this isn't an issue if the object that you're trying to photograph is reasonably bright, but if you're trying to get a faint and diffuse nebula or a dim star's spectrum, well, that's a bigger problem. And this is why Harvard's Bruce telescope was designed to take wide-field photographs, as that configuration gave much lower f-stop numbers and shorter exposure times, leading to what's known as faster photography. Newton's reflecting telescope design, therefore, is really pretty brilliant in part because since the light travels down the tube and then back up to a second mirror that reflected it out the side of the tube, that meant that the length of the tube could actually be shorter. Soon after Newton's reflector was revealed, a different design was put forward by the French priest and physicist Laurent Cassegrain, probably in the year 1672, though there's some debate about that. This configuration had the typical curved mirror at the bottom of the telescope, but in place of a flat secondary mirror that directed the light out the side of the scope near the open end, Cassegrain's design used a second curved mirror to direct the light back down through a hole in the primary mirror and out the back of the telescope. And by the way, if this seems a little confusing, we'll post pictures to this at our website at thescientificodyssey.typepad.com. The reason that this is a really good design is that since the light is directed to the bottom of the telescope, the observer doesn't have to climb some elevated viewing platform the way that Herschel or Parson had to when they were operating their really massive telescopes. The downside, on the other hand, was that since each mirror only reflected about 50% of the light that hit it on a good day, less than 25% of the light that came in the front of the telescope would actually make it to the observer. And this really limited the design's effectiveness for some time. Now, to get back to the Melbourne Reflector, I said earlier on a good day because the other drawback the metal mirrors always have is that they tarnished relatively quickly. And so what you would always do is that you would have multiple mirrors actually made for any telescope. Usually two, but sometimes more. Herschel sometimes was known to have 3 or 4 of these things. But usually you'd have 2, and so what you do is you pull one of the mirrors out of the back of the telescope, put the other mirror in, and then you'd repolish that first mirror. And then you would put that in and pull the second mirror out and repolish that, and you would be able to trade these back and forth, repolishing each time to deal with the tarnishing. The problem, of course, with the Cassegrain design now is you would have to pull 2 mirrors out that would have to be repolished to an exactly specific shape. In the case of the Melbourne telescope, that meant that they had to be sent all the way back to Ireland where they had been made for a repolishing, and then returned, a process that could take 2 or 3 years and thus was seemingly very impractical. Therefore, when the observatory's director decided to short-circuit that a little bit and tried to do the repolishing job on site, he seems to have damaged the mirrors, rendering the telescope more or less unusable for research after that. And this experience doomed the reflector, at least during that period after about 1868, 1870 for a while, as a research instrument. But this didn't mean that reflectors were done. During the 1950s, research was being conducted on new ways to make mirrors for various commercial purposes. Mostly, you can think of putting a mirror up in your bathroom. And it was the German chemist Justin von Liebig who developed a process that allowed a thin layer of metal, usually silver, to be annealed to the surface of glass. In 1856 and 1857, two different researchers, the German astronomer Carl August von Steinheil and the French doctor Léon Foucault, figured out that Liebig's process could be used to create astronomical mirrors that were easier to work with than those being used. More importantly, the silver reflected 90% of the light that the older alloys didn't, and it also didn't absorb most of the colors, which allowed for all of the light to be observed. Foucault also developed a better way to test a mirror's shape, thus allowing for the creation of extremely precise mirrors in a significant improvement over the more or less trial and error methods that had been used since the time of Herschel. Unfortunately, these new technologies came along just as the Melbourne Reflector was being planned, and so they didn't make it into that design. It's one of the things that sometimes happens in astronomy. Newer technologies often don't make it into designs because astronomers generally tend to be pretty conservative when trying to construct their instrumentation. With these advances in mirror technology, new designs for the telescopes that employed secondary and in some cases tertiary mirrors now became practical, as the mirrors reflected most of the light that entered into them. This allowed the telescopes to be shorter. Additionally, as we've mentioned in an earlier episode, the fact that the primary optical element, always the largest and heaviest thing in the telescope, was at the back or the bottom of the scope, created additional advantages. The first of these was that the mechanical systems being developed to move the telescope didn't have to support a weight that was far away, as was the case in refractors where the primary lens was way out at the end of the telescope. In other words, the weight had a very small lever arm, as physicists or engineers like to say. The second was that given these new geometries, the primary mirror didn't have to be as thick or as heavy for a given side as the lens did, and so it didn't flex or change in shape. Now, to be clear, it would take a while for the reflecting telescope to overtake the refracting instruments that were being built in the period from the 1850s onwards. First, the technologies had to be fully developed, and that always takes a little bit of time. The industry to make the glass that could be used for both lenses and mirrors had been around for a long time, and thus could be used to make what were known as blanks, or big glass discs that could be ground into the correct shapes, but the number of people who could do the silvering processes was very limited to begin with. Second, as you can imagine, the casting of, say, 2-foot large glass blanks or discs that were several inches thick wasn't really something that was in high demand. And so there were only a few craftsmen worldwide who would or even could take on such projects, which required the sort of the pouring and solidifying of a large quantity of really high quality, defect-free glass, and then shaping that glass precisely to a given form through grinding. As such, for a long time, projects asking for lenses often got priority, though, as we saw in the case of the Bruce telescope, even those sometimes got pushed off. Nevertheless, if one had enough money, reflecting telescopes could be made, and in the late 1800s, there was a desire to create them to do work in the growing field of spectroscopy and, in time, astrophotography. To understand this, let me remind you of the great strength of reflectors at this time, and that was the fact that they focused all of the light the same. And after the invention of the silvering process, that really was almost all of the light. All the wavelengths that came into the telescope and hit the mirror were reflected off the mirror and into the spectrometer. The lenses of refractors had the drawback of focusing different colors of light at different places, a problem mostly, but not completely, solved by using doublets of crown and flint glass. And they also had the problem of absorbing certain wavelengths of light. If you wanted to do spectroscopy, it's really not a good thing if your primary lens absorbs all of the frequencies of light, say in the yellow or blue part of the spectrum. Because of the way they worked, mirrors didn't do this, and so as spectroscopy becomes a bigger and bigger thing, reflecting telescopes start to become something in greater and greater demand. So, the first person who seemed to really realize the advantages of reflecting telescopes was Henry Draper, who had a 20-inch reflecting telescope constructed for his private observatory. Prior to his death, he used this instrument to get the first spectrum of the Orion Nebula and began collecting, with his wife Anna, the photographic spectra of about 24 bright stars. Upon his death, this work was transferred to the Harvard College Observatory under the direction of Edward Pickering, and in time the telescope followed. As we mentioned in those episodes on the HCO, this instrument was a difficult one to use, and it took Pickering and his staff a long time to get it to work. And this is something that we'll encounter with reflecting telescopes on and off as we go forward. They're really hard to work with at this point in time, not as easily as the refractors are, and so astronomers who have long experience working with those refractors will have a hard time adjusting. The other large reflector built at about the same time was an instrument constructed by Andrew Annesley, or AA, Common of London. Now, Common was a sanitary engineer by training, but he really was an amateur astronomer at heart who enjoyed tinkering with telescopes, and he quickly grew to like the advantages of reflectors, especially when it came to astrophotography. He was aware of the new silvering technologies that had been developed in Germany and France, and in the 1870s began a process of constructing larger and larger reflectors to test those various technologies that he had available to him. In 1876, he hit his limit in trying to create a 17-inch mirror, and subsequently he farmed out the construction of his design ideas, at least in terms of the mirrors, to George Culver, who had a lot more experience with working with glass. In 1879, Culver made a mirror that was 36 inches in diameter, and Common mounted it in a Newtonian arrangement. While the telescope was a wonder in that Common used it to do a number of really innovative things, including taking the first photographic image of the Orion Nebula, it suffered from the drawback of having a really dodgy mount. It wasn't as stable, and it was really hard to work with as a lot of people wanted. Nevertheless, Common sold the telescope to the British politician Edward Crossley, who had planned to use it to establish a private research observatory on his land. However, owing to the poor mount, he could never get the thing to work properly. Crossley soon realized that, as had been the case with Parsons in Ireland, England's weather, at least in his area, and the climate there weren't exactly the best to be trying to do research-grade astronomy in. Thus, in 1895, he gave the telescope to the University of California's Lake Observatory, where it would be installed, not work, and then be forgotten for 3 years until the right man came along. And that man was James Edward Keeler. Keeler was born on September 10th, 1875, in LaSalle, Illinois, near the Illinois River in the northern part of the state. While his family was from New England originally, having deep roots that went all the way back to the Revolutionary period, leading Keeler's wife to say that James was the quintessential Connecticut Yankee. Keeler's parents had actually moved to Illinois after his father had tried to make his fortune in the California gold rush of the late 1840s. After what can only be described as a disastrous trip to the goldfields, William Keeler had returned home to his wife and then moved to Illinois to work as a watchmaker. By the time James was born, the elder Keeler was prosperous, and when the Civil War broke out, he used his influence to obtain a commission in the Union Navy as an assistant paymaster. He was assigned to the first ironclad, the USS Monitor, and on several occasions acted heroically, including during the encounter with the Confederate ironclad, the Merrimac. After the Monitor sunk off of Rhode Island, William served with distinction on the vessel the USS Florida, being wounded in action several times as part of the blockade of the southern harbors, especially those in Florida. After the war, William moved his family to Mayport, Florida, but not before his son had had a chance to see, at age 11, the 1869 eclipse, with the path of totality passing directly over La Salle, thus igniting a passion for astronomy in the young man's mind. While in Florida, James was homeschooled and soon found that he enjoyed poring through his father's stacks of Scientific American issues. He soon ordered a pair of 2.5-inch lenses from a manufacturer that advertised in the magazine, and with the telescope he built from them, he observed and made drawings of the moon and planets. One of the things that's really interesting about Keeler is the number of individuals who note, as you go forward, his exceptional quality of illustration. It's kind of like those biologists of the same period of time who were so phenomenally good at making super accurate renditions of plants and animals and all sorts of other things that they encountered in the wild. Keeler had that same ability, but instead of it being some flower or some bird, he was able to draw things like, what he saw through the telescope at the surface of the moon, or later in his career, the corona of the sun, or any number of other things. Now, during this time, William Keeler had once again made a few connections, including connections with one wealthy family by the name of Rockwell. The Rockwells hailed from the same part of Connecticut as Keeler's ancestors did, and the two seemed to hit it off pretty well when the Rockwells came down to Florida for vacationing for the warmer winter climate in the Sunshine State. So, in 1877, through this and a few other connections that he had, William managed to get his son a spot at the first American scientific research university, the Johns Hopkins University. Now, while the young man with his relatively rustic backcountry upbringing wasn't a good fit for the cultured blue bloods of, say, Harvard or Yale, he settled right in there at Baltimore. The faculty at Johns Hopkins were young, well-trained in the European scientific tradition, and eager to break the mold of the American university founded on the British college model. In this environment, Keeler's natural scientific talent was nurtured in spite of his, as one classmate called it, cracker drawl. In the summer after his freshman year, Keeler was able to accompany a group to observe the 1878 solar eclipse in Colorado. This expedition was led by Edward Holden of the U.S. Naval Observatory, a man who would continue to be a big part of Keeler's early scientific career. He also accompanied a team led by Samuel Langley to measure the intensity of solar radiation from the top of Mount Whitney, the tallest peak in what was then the United States. His work during this eclipse trip, observed of course from the top of a hotel in Central City, Colorado, as well as the things that he did on the solar expedition, at times operating the most sensitive scientific equipment there, earned him praise from all involved, and when he graduated he was offered an assistantship to work at the Allegheny Observatory under Langley's tutelage. Langley would mentor the young man, at least for a period of time, until a few years later he would take up a position at the Smithsonian that would allow him to pursue his dream of building a flying machine in competition with a pair of bicycle mechanic brothers from Dayton, Ohio. While at Allegheny, Keeler participated in the observatory's observations of the Venus transit in order to more accurately establish the Earth's distance from the Sun. After his time in Pittsburgh, working for Langley, Keeler then did a year of postgraduate study in Germany, first at Heidelberg, and it is here that he really began to become interested in spectroscopy, a technique he had first learned while on the solar expedition, and that had been further honed under Langley's supervision. Keeler was able to attend lectures given by Robert Bunsen on the topic. Later, he toured Germany before attending lectures by Helmholtz in Berlin over the winter of 1883 and 1884. Again, the focus here was on the analysis of spectra, and during this time, Keeler learned a variety of techniques that would serve him in good stead over the rest of his career. Upon his return to the United States, he went back to work for Langley, though only for a couple of years, before Edward Holden offered him a job at the newly established Lick Observatory on Mount Hamilton in California. Keeler was Holden's first professional astronomer hire, and it's absolutely the case that he was by far the most talented of the astronomers that Holden hired in his initial run. He was brought on to use the brand new 36-inch refractor, and in 1889 he was the first to observe what is known as the Inky Gap in the ring system of Saturn. He worked at Lick for about 5 years before being recruited to become Langley's replacement as the director of the Allegheny Observatory. The reason for his departure from Lick had to do with the ongoing conflict that he and nearly every other astronomer who worked at the facility had with Holden, who basically ran the place like a military camp and often interfered with or even tried to take credit for other astronomers' work. The other reason he left was that he wanted to marry Cora Matthews, the niece of the wealthy director of the Lick Trust. While his astronomer's salary was certainly enough for the two of them, it didn't provide a housing allowance for a wife up there on the mountain at Hamilton. And so, when the position in Pittsburgh in 1891 was offered, he took it and soon after got married. Now, for Keeler, going to Allegheny was, astronomically speaking, a step down, at least technically. The telescope there was much smaller, and the observing conditions were vastly inferior owing to the steel plants that were, belching out all kinds of smoke and waste and all sorts of stuff into the atmosphere. So what Keeler did was innovate. It's interesting to contrast what was going on in Harvard at this time with what Keeler was doing. Harvard was, in a sense, sort of an astronomical data factory. While there was certainly some innovation taking place, the main focus at Harvard was to take tried and true methods and use them to gather and analyze just mountains and mountains of data. Keeler, on the other hand, was more like the artisan working in a shop, coming up with new ways to do things that would help keep him in business in the competition with the factories that could mass produce information. In this way, Keeler became the world's foremost spectrographer, coaxing data from the telescopes in Pittsburgh that no one else would have been able to. His best-known work from this time was the observational determination that James Clerk Maxwell's theoretical calculations that the rings of Saturn were made from tens of thousands of small chunks of matter, probably ice, all orbiting the planet according to Newton's laws, was in fact correct. This, however, was but a small piece of the work he did at Allegheny, among a whole lot of other things, including establishing rotation rates for some of the planets and calculating radial velocities of the stars, how fast they were moving towards and away from us. However, as is so often the case in these sorts of stories, there's a point past which, without a serious upgrade in equipment, the artisan just can't compete. Keeler realized this when he was asked to test a spectrometer that had actually been built for the 36-inch refractor at Lick. So superior was the instrument that he realized that no number of tricks and techniques and innovation and just being very clever would allow his work to even begin to approach that which would be done with the spectrometer that he was testing. Fortunately for him, Holden had just made the decision that would cost him his job and set up the conditions for Keeler to change astronomy. Holden's big mistake was in obtaining the Crossley reflector, having brought it to Mount Hamilton, and then installing it and then trying to make his astronomers use it. The instrument, with its shaky mount and unfamiliar configuration, was, at least to the staff at Lick, impossible to use, and so was soon abandoned. The whole debacle was sort of the last straw for the staff, and in a word, they revolted. The Board of Trustees, seeing that Holden had lost the confidence of his staff, was asked to resign. This, of course, opened up a position, and Keeler quickly applied, using connections that he had all over the country. When the citizens of Pittsburgh heard that their popular and hugely well-respected director was thinking of leaving, they tried to raise enough money to both offer him a better salary and build a new, state-of-the-art telescope there in Pittsburgh. Fortunately for history, they failed, and in 1898, Keeler went back out to California and into the mess that Holden had created. As great as Keeler's strengths as an observational astronomer were, they may actually have been exceeded by his talents as an administrator and manager of people. Just as had been the case in Pittsburgh, Keeler very quickly won the respect of the frustrated astronomers at Lick. This basically was most likely because of his decision not to ask for any time on the big telescope. Now, both as the observatory's director and on the basis of his reputation as really truly a great astronomer who had tested the newly installed spectrograph, he would have been well within his rights to claim the lion's share of the time on that 36-inch refractor. It was the big instrument at the observatory, and as the director, you would have thought he'd have said, "Hey, I'm going to take my time on this thing." Instead, he decided that W. W. Campbell, the man who had been using it, would continue to do so, and instead he would do his investigations using the Crossley reflector. Now, as we've documented, this was quite a monumental undertaking, but Keeler saw that given the nature of reflecting telescopes, there were likely going to be some real advantages for the type of work he wanted to do if he could get the instrument working. After about 4 months and a lot of redesigning of the mount, he did in fact get the telescope running, and soon discovered that it could do everything he imagined and more. The spectra taken from the Crossley were remarkably complete, and the long exposure photographs were unparalleled, something he demonstrated when observing a comet in a way that no other observatory in the country was able to. Soon he was imaging faint nebulae, and as his exposure times got longer, he began to notice that heretofore undiscovered spirals appeared on his plates. As he began counting them, he began to realize that no matter where he pointed the Crossley, these spiral nebulae would emerge out of the darkness to be recorded on the photographs like moths drawn to a lantern. In less than a year, Keeler would estimate that the number of these faint spiral nebulae was in excess of 120,000, with his belief actually being that the 9,000 spiral nebulae that actually were in catalogs that had been recorded and documented to that date represented that less than 1% of the actual total. In other words, he thought there were millions of these things. And what we know now, of course, is that he was vastly underestimating the number. However, just as importantly, he began sending these images that he was taking to other observatories and astronomers, an act that began to convince many, most notably one George Ellery Hale, that the era of refractors was coming to an end, and the era of great reflectors was just beginning. One, of course, has to wonder what would have happened had Keeler lived past his 43rd birthday. There are those who believe that it would have been him, rather than Hubble, who would have collected the data to show that these galaxies, these spiral nebulae, were actually things that resided outside of the Milky Way, and that the universe was expanding. Unfortunately, his habit of enjoying tobacco, combined with the harsh weather at the top of Mount Hamilton, led to pleurisy of the lung, along with a likely case of emphysema, if not lung cancer. And while trying to recuperate in San Francisco, he died from the complication of 2 strokes. His directorship was taken up by W. W. Campbell, who we discussed in an earlier episode, and his work with the Crossley was taken over by Heber Curtis. While the legacy he left at Lick is incalculable, what is more important to astronomy was his demonstration that for the type of work that was going to be done going forward, the best instruments would be reflecting telescopes, and nowhere was that lesson more keenly understood than at the Yerkes Observatory in Lake Geneva, Wisconsin. The Yerkes Observatory, built in 1897, was the brainchild of George Ellery Hale. As we're going to spend an entire episode on Hale and his founding of not one, but 2 world-class observatories, I won't spend too much time on that here, other than to say that Hale had originally found funding for the facility by promising businessman and sometimes con man Charles T. Yerkes that he would build the largest telescope in the world if Yerkes gave him the money to do so, and, of course, by promising to name the observatory after him. In the end, Yerkes not only provided money for the telescope, but also for the rest of the observatory, constructed on Williams Bay, overlooking the lake. Now, the instrument that he promised to build was actually a 40-inch refractor, and it was the largest in the world. And it was really quite remarkable, but as grand as that instrument as it was, it showed really to both Hale and anyone who was paying attention that the time of refractors was at an end. The problem was that the telescope was all of those things we discussed earlier. Most importantly for research, though, the weight of the lens, supported only at its edges, caused the lens to sag slightly differently in different orientations, thus causing the glass to deform ever so slightly and distorting images and data. As Hale began to look towards his next project, he realized that there was really no going forward with larger refractors, and thus he began to look at reflectors as a better solution. The biggest reason for this had to do with a smaller telescope that had been constructed at the Yerkes facility. Hale and Keeler had long been friends as well as colleagues, the two having originally bonded over their shared work in solar astrophysics, and then their idea to found a premier journal for the emerging field of astrophysics, something that still exists today called the Astrophysical Journal. One thing that they had discussed prior to Keeler's decision to join the Lick Observatory was whether the time had come to re-examine the role of reflecting telescope at American research observatories. These conversations, along with a trip Keeler made to England to see the photographs being produced by a relatively large reflector there, likely had a large role in his decision to work with the Crossley when he arrived at California. For his part, though, Hale had managed to get a hold of a pair of 24-inch glass blanks, and he decided to turn them over to his partner and ace in the hole, George Willis Ritchey, to see what might be done with them to build a reflector for the Yerkes Observatory. Now, Ritchey was a really interesting guy. His grandfather had immigrated to the United States during the Irish potato famine in 1841 and had settled in Ohio with a wife and 3 sons. A mechanic by training, Grandfather George had bought a mill, and soon the family was on relatively sound footing. In 1850, his eldest son, James, had finished all the school he was going to do, and so he and his father opened up a furniture shop in Pomeroy, Ohio. In 1864, James's son, George, named for his grandfather, was born on December 31st. Initially, the grandson followed his father and grandfather into the cabinet-making business, but it turned out that he had a little something more in mind. His namesake had been something of an amateur astronomer and had passed the love of the stars on to the grandson. And as is often the case in immigrant families, after a generation or two have come and settled in, the next generation is sent off to college to move up the socioeconomic ladder. And so it was with the younger George, who, with his mechanical experience, went off to the University of Cincinnati, studying first drawing and design, and then astronomy. As part of his time there, he worked as an assistant at the observatory, soon reading the writings of Henry Draper and A. Common on telescope design and construction. At home, during this period, he began making mirrors. In 1888, the younger George moved to Chicago to pursue work and was soon teaching at the manual training school there. 2 years later, as a result of this, Ritchey met Hale, and the two soon found that they had a lot to discuss. As Hale worked to bring the observatory together, he realized that due to its distance from Chicago, which was some 72 miles, the observatory would need its own workshops and technicians to staff it, and so he hired Ritchey to be the main optician and telescope designer and builder at the facility. One of the projects the two undertook was to create a reflecting telescope that was sort of a proof of concept for some ideas that Hale and Ritchey had for something a whole lot bigger. This was a completely new telescope design based not on Newton's ideas, as had been the case for almost every reflector built up to that point with the exception of the Melbourne Reflector. But instead they decided to use a design suggested by Cassegrain. The 24-inch reflector thus created, while smaller than the Crossley, was by 1901 producing higher quality images even though it was operating in pouring seeing conditions, and this was due mostly to its more stable and workable design. This was all the proof that Hale needed, and he soon convinced his father, a fairly wealthy man, to fund the purchase of a pair of 60-inch glass blanks to make the next generation of instruments based on Ritchey's work with the 24-inch telescope. Hale's hope was that he would create the telescope and then sort of sell it to the University of Chicago. However, during the next 2 years, Hale's daughter developed asthma, and her doctors recommended that she be relocated to a better climate, something a little drier and warmer than what one usually found in Wisconsin, especially during the winter. Hale and Keeler had often discussed building a new observatory in the mountains of Southern California, and so when Hale visited there, he was convinced that he needed to move to the little town of Pasadena. Above the town was Mount Wilson, or at least at the time it was actually called Wilson's Peak. Hale would change the name. And so Hale was able to convince the Carnegie Institution to build both a solar observatory and later a giant telescope at its top. However, the thing that was really interesting was it soon became apparent that the University of Chicago was no longer willing to pay for those great big mirrors that Hale had had his father purchase and that were being made at that time. And so Hale decided to try to convince the Carnegie folks to buy those instead, and was able to do so. With that done, he brought Ritchey over from Yerkes to join him at the new Mount Wilson Observatory with the goal of building the most advanced telescope ever created. Now, as this was being done, with Ritchey grinding the mirrors using a new machine that he had developed for just that purpose, Hale began working the local community there in Southern California to try to find funding to build an even larger instrument. As the 60-inch telescope was being constructed, again built on the Cassegrain design Ritchey had mastered, Hale procured the funding for an 100-inch behemoth instrument. It's here again that we should probably spend a little bit of time on some technical details. In the years since the construction of the first larger reflectors, a few other designs had actually been created to allow for additional functionality for these types of instruments. One of these is known as a Cuda focus configuration, which allowed the light from the telescope to be directed out through the mounting arms of the telescope by using a tertiary or third mirror to a stationary instrument package. This configuration allowed for very large instruments such as high-order spectrometers and large plate cameras and other kinds of things to be used without having to try to attach them to the telescope itself. Ritchey's design was particularly innovative in that it allowed a technician to set the 60-inch telescope in any one of 4 different configurations as might be dictated by the work that needed to be done, for an astronomer. At this point, though, another issue began to rear its head, and that was that making pieces of glass in a disc shape larger than 60 inches inside was beginning to be extraordinarily difficult. While the blanks for the 60-inch had come out well, that had only been after several failed attempts. The other problem was that the glass of this period had a somewhat large expansion coefficient. This meant that if the glass wasn't kept at a reasonably stable temperature, it might just warp a little bit, and in doing that, it would distort images. To combat this, Ritchey had designed his domes to be insulated and almost airtight in some respects, so as to keep the mirror at a relatively stable temperature and shape. In other words, the mirror would sort of cool down at night, and then the whole dome and observatory structure would be all buttoned up tight, and even though outside of the dome the temperature might get pretty warm, inside the dome it would stay relatively cool, and the mirror would stay mostly the same shape. The problem is that he could see, however, that as mirrors got larger, this could be a bigger and bigger problem. The 60-inch telescope saw its first light in 1908, and it would be used to do a huge amount of astronomical research, including the observations made by Harlow Shapley that we discussed a few episodes back. So, with the success of the endeavor and the funding in place for an even larger 100-inch reflector, Ritchey began to tackle the problems he foresaw arising with trying to deal with that kind of a mirror. His solution was to create what he called a cellular mirror. In this case, or in this sort of approach, there were 2 thin pieces of glass that would sort of sandwich a hollow honeycomb central structure that would allow for air to flow between the two pieces of glass and thus keep the temperature of the whole thing fairly constant. This, however, was kind of too cutting edge an idea for Hale, and he rejected it, opting instead to go with a solid mirror of 100 inches, thinking that, the mirror manufacturers, the glass manufacturers themselves, could work out sort of the problems and get it all sorted out. This decision began a long deterioration of his relationship with Ritchey. There's no question that Ritchey was a brilliant and gifted telescope designer, and also a very good observational astronomer. The problem was that the other thing he was an absolute perfectionist. I sometimes tell the story that my mom used to say this sort of thing that she had learned from her grandfather, and that was, if you're going to do a job, do it right, or don't do it at all. As much as that irritated me, it's exactly the sort of thing I can imagine Ritchey yelling at some poor shop technician, except that when he said right, what he really meant was perfect. What this meant was that when things didn't go the way he thought they should, he tended to not react really well. Hale, for his part, who struggled with depression, often put off dealing with Ritchey, or when he did deal with him, he tended to dismiss his most innovative ideas out of hand, and this set up a real sort of conflict that would fester and grow over time. So, while the 60-inch telescope was being built, Hale had a French glass company make the 100-inch blanks, the huge discs that were, 8 feet across, and that weighed 4.5 tons each for the new Hooker telescope, as it was called, named after, of course, the individual who funded its construction. When these blanks arrived, however, they turned out to be seriously flawed, just as Ritchey had feared they might be. In the glass were thousands of tiny bubbles that sort of permeated the structure. Moreover, the glass wasn't actually completely fused, so that when viewed from the side, it kind of looked like a 3-layer cake, which seemed to jeopardize the glass's ability to expand and contract evenly if its temperature changed. Hale ordered that the job be redone, but the company had no additional success. It turns out that at that time, technology for making glass just wasn't good enough to create pieces of glass that were uniform at that incredible size. As a result, Hale decided to gamble that the bubbles were deep enough that the grinding of the lens to a parabolic shape wouldn't cut into them, and also that the expansion issue wouldn't be such a problem for a disk that was that big. He kind of gambled that the thermal inertia of that big a piece of glass would be such that the disk of the glass wouldn't expand or contract all that much. Hooker, the man who had funded the project, and Ritchey were both dead set against this, and soon things devolved to the point where Hale actually had a nervous breakdown over the whole thing. As a result of this, and because he was kind of a company guy at least at this point, Ritchey decided to go ahead and follow Hale's instructions, and over the next 6 years, while Hale struggled on and off with mental health issues, Ritchey turned that blank into an exquisitely shaped mirror. In 1917, the mirror went up the mountain, and 4 months later was installed in its mount, ready to test. When Hale climbed the steps of the ladder to see the view through the eyepiece, he cried out in horror as Jupiter, the first thing ever imaged by the telescope, was seen in 6 overlapping images. It seemed that the mirror was badly flawed, and that Ritchey's warnings and concerns had seemingly been correct. Then Hale recalled that the workmen, still installing various things on the observatory dome, had left it open all day, causing the telescope to really warm up. In this case, the mirror would have warmed far beyond its typical operating parameters and thus would be expected to have distorted. If that had been the case then, Hale reasoned that the images would recombine into one image as the telescope cooled down. And so at 2:30 a.m. in the morning, Hale and his companions returned to the scope, and when they looked again, this time at the star Vega, they found just one perfect image, glorious in its clarity. As the United States entered the Great War, work on the telescope more or less stopped throughout 1917, as Ritchey and others were pressed into various activities, things like making lenses for different types of military instruments. With those delays and news of the image problem, Ritchey became convinced that the telescope would fail and once again tried to convince Hale to replace the mirror with one made according to his cellular design. When Hale again refused, Ritchey began spreading the word about the impending disaster, at least as he saw it, and when he contacted Hooker about the whole thing, Hale was forced to fire him for insubordination in 1919. The 100-inch telescope, of course, never suffered from the issues Ritchey feared that it would, and it was used by Hubble and Humason to show that Lemaitre's expanding universe was the correct model, in addition to any number of other things. For his part, Ritchey would land on his feet at his ranch east of Pasadena, and in the 1920s he moved to France for a time to work with the French astronomer and telescope maker Henri Crétin to develop a new telescope design. The two worked to develop Ritchey's cellular mirror idea along with additional refinements to the Cassegrain design. In 1930, Ritchey moved back to the United States and designed and built a new 40-inch reflector for the U.S. Naval Observatory. Initially, though, the results for this instrument were really disappointing. The images were pretty mediocre. However, when the instrument was moved to Flagstaff, Arizona in the 1950s, shortly after Ritchey's death, and away from the lights of Washington, D.C. and the humidity of the Potomac, it produced images and data that far exceeded any expectations Ritchey or anyone else had had for it, thus validating his design ideas. Ritchey's ideas would be vindicated by more than just that, however. As we'll discuss down the road here a bit, while Hale would manage to build an even greater telescope, the 200-inch reflector at Palomar, it was clear by that time that the limit for large, single-piece mirrors had been reached. The last telescopes of significant size built using this model were the Mayall 4-meter telescope at Kitt Peak in 1973 and its twin, the Blanco telescope at Cerro Tolo in Chile in 1974. Since then, every telescope that has been built using some form of Ritchey's design, and this includes the Hubble Space Telescope. In closing, I would be remiss if I didn't also mention that in addition to being the world's foremost telescope designer, Ritchey was one of its best astronomical photographers. His images, especially with the 60-inch telescope, were unparalleled in his time. And I found that as I was doing my research for this episode, a whole bunch of his personal notes and personal images had actually been offered up for auction in 2014. The asking price for the collection started at $500,000, and while I wasn't able to find the final bid price, I'm sure it was far north of that. As we bring this episode to a close, I really want to give a shout out to the folks at the Northern Nevada Science Alliance. They've been big supporters of the Odyssey, and they're doing great work in Reno with science outreach. If you're listening to this show from that area and haven't had a chance to connect with them, I hope you'll Google, look for them, and find out how you can be a part of their next event. I'm sure you'll really enjoy it. They're great. For those of you who have recently joined the crew, I hope you're enjoying the show. If you've got comments, please feel free to leave them at our website, thescientificodyssey.typepad.com, or on our Facebook page. You can also email me at cldavies@mac.com or follow me on Twitter at @ChadDavies. We're still taking comments/votes on the idea of an Einstein biography, so please let us know your preference there. We really would like to find out. Also, if you haven't done so, we'd sure appreciate you leaving us a strong review on whatever service you use to enjoy the podcast. I can tell you, it helps us to get the word out by moving us up in the various rankings in whatever country you happen to be listening to this in. Lastly, let me say a few things about where the show's going in the next few weeks. What we're going to do is we're going to continue to look at some of the figures that have gone into making this period that we're studying so explosive in terms of the growth of astronomical knowledge. The difficulty with this is that a lot of the figures that we're going to be talking about aren't as well known. And so it's a little bit hard to get good resources. And that's actually starting to take some time. And so it may turn out that things get a little out of whack chronologically as I wait for those resources to come in. In the worst case scenario, there may be a week's delay in having an episode come out, but I'm hoping that that's not going to be the case. Cross your fingers for good interlibrary loan. I'll certainly let you know if that's going to happen, but as several folks on the various forums have said, whether in relationship to this podcast or others, they'd rather have a show come out late than it just be a reformulation of material that one can easily find on Wikipedia. And I certainly agree with that. With that being said, I hope to do a good biographical look at the life of George Ellery Hale next week, followed by a show or maybe two, depending on how much there is actually that I dig into it, on the Lowell Observatory and the work that's done there in the week after. Now, if I'm not mistaken, that's going to take us to about 150 episodes total and get us pretty close to the 3-year mark for the show. And I hope you'll all join me in celebrating that. So until then, full sails on your journey.